Hello everybody. I'm just going to make a quick video showing how to work out the 7 different problem solving questions in the AutoCAD quick exam. So I'll load that in and we'll start off. So you can see in the menu we now have problem solving as a 4th option, and these are the 7 problems to work on. So these first couple are trigonometry problems. There's a vector summing problem, which is in a sense kind of a trig problem also. Area solve is just looking at the area of a bounded region, the volume of a sphere, centroid of a region, and also the second moment of area of an I-beam type section. We'll start at the top and work our way through. So the angle solve problem. If we have a triangle with side lengths 33, 10 and 29, and we're asked to determine the internal angles of the triangle, how can AutoCAD be used to help the solution of this problem? The first thing you'll need to do is draw a line. I usually draw a line with length equal to the longest side in that in this triangle. And now what you need sort of attached to this line, you need 2 other lines of length 10 from one side and length 29 from the other. But we have no idea which angle we're going to draw this at. So basically need some sort of function that's going to describe every possible length 10 from this point. And that of course is a circle. If I have a circle of radius 10 connected to that point, this end of the side of the triangle, and another circle of radius 29 connected from this point, I can use the intersection of those 2 circles to find me lines which are 10 units long and 29 units long to make up my triangle. So there's the triangle that's needed. What we need next is the dimensions. So you can apply angular dimensions. You'll notice that the answers to these problems are given to 2 decimal places, and by default the dim ang setting only gives you an integer value. You can change that in dim style. So if I go modify and I want precision 0.00, I'll change this precision while I'm here as well, just making sure that we can measure lines and angles to the right amount of decimal places. And then supplying these angles, we have 58.18, 104.78, 17.04. So where are we for that one? That's answer 2. Hit QE when you're ready, supply the correct answer, and the program tells you that you were right. Okay, so that's how you solve for the angles of a triangle with known side lengths. What about in this particular case? We have one known side length and 2 known angles, but unknown remaining sides. So how do we go about this one? Same sort of start. Start with drawing a line which has the length which is provided there. Making it a horizontal line will also help in that I can, for one of the adjacent angles, this say 88 degrees, I can simply hit tab to specify 88 degrees is the angle I want to draw a line at. And the length of this line is either going to be too long or too short, but we can trim that off in a moment. So that means that this internal angle, I'll show this, 88 degrees in there. Now we want this other angle in here to be 43 degrees, but I can't simply hit tab 43 because this line is going to be on the wrong angle. So we need the angle in here to be 44 degrees. So what I can do, if I draw a line from that point there, I'm just going to draw it horizontally back this way, then select that line and rotate it through 43 degrees. Remember, I want this to rotate clockwise, and AutoCAD measures angles as anti-clockwise positive. So negative 43 will provide the rotation I need. Now we'll just check that all of this triangle has been drawn correctly. So there's the 43 degrees, there's the 88 degrees. We have the side length 23 there. So if we trim off the other parts of the triangle, the unneeded parts of that triangle, can then find that the remaining lengths, we have 20.78 on that side and 30.46, 20.78, so that's answer 6. It's a good idea to keep changing your layers to put sort of dimensions, construct an actual solution to the problem, like providing some sort of working. So this triangle is very intelligible. I can see all of the details that I need to work out all of its properties, and at a glance you can see that you've made some sort of solid attempt. So as I said, answer 6 is right here, and we can move on to the next problem. So this is now summing vectors together. So this problem asks, 3 vectors have magnitude 35, 29 and 41, and the bearings of these vectors are 344 degrees, 278 degrees and 207 degrees respectively. So for those of you who are wondering, the respectively part, that means 35, the first term, corresponds to the angle in the first term. 29 units long is at 278 degrees. So first to first, second to second, third to third. And the other term that may be giving some confusion is bearings. What do we mean by a bearing? So AutoCAD measures angles along the x-axis as 0 degrees. If you see in the bottom left corner, I have my axis system here. So the positive x-axis is 0 degrees, and we have that anti-clockwise is positive. So a bearing of 344 degrees would be down there. So it's gone from 0 all the way around this 344. So if I want to supply these lengths, I can say I have a length of 35 at an angle of 344. It's important when you're working out these problems to make sure that your cursor position is higher than your starting point. If, for example, I bring my cursor down below, you'll see that the 60 degrees I'm measuring there is going to be a clockwise measurement. So if I were to try and enter my next line at a length of 29 and an angle of 278, but I left my cursor below my start point, you see that this length of line up here, it doesn't really look like 278 degrees. Remember, if this is 0 and we're measuring anti-clockwise positive, 278 should be down here somewhere. So this will give you an indication. Just by looking at the lines, you'll see that something is wrong. But if you, as I said, make sure that your cursor is above the starting point. When I specify a length of 29 at an angle of 278, then my drawn vector is going to be in the right direction. The last one we have in this case is a length 41 vector at an angle of 207 degrees. And if this was the starting point here, we've basically gone head to tail, so we've got a vector pointing this way, vector going this way. So this is the flow of the vectors, which means my final vector is down this way, giving us a length of, if I change here, where are we? I'll see if I can get a bearing as well for this. Dimensions. So we have, I'm getting 88.84, but that's plus 90 here and plus 90 down there. So we're at something like 280 odd degrees, 268 perhaps. And the length, if I run the aligned length of this completed vector, we have a length of 56.99. So we're corresponding to this value. Actually, no, probably supplying that angle is just confusing in there. If you need to determine the angle, you can consider. So I'm measuring 89 here between 0 and my shown bearing. If I take 360 and take 89 away from that, that gets me my angle of 271. In any case, measuring either the angle or the length allows you to find the final answer, which in this case is answer 7. Okay, so that's how you solve the vector problem. You just draw each vector head to tail, find the total length, and then select your final answer. What about this area problem? So in this problem we're asked to define a polygon which has vertices, that is corners, vertices here, corners also, at points 0, 0, 425, so these are XY positions, 23, 17 and so on. So I could create these points down near the origin at 0, 0, or because I'm working within this box I can move the origin to the actual box itself using the UCS command. So it's UCS, and I'll move the user coordinate system in here. Now I need to create a polygon with these points, so I'm going to use a polyline, but if I start the polyline command, my first point I can supply as XY position, but all my subsequent points I have to supply with length and angle. So it's actually helpful in this case to instead supply circles. If I supply a circle at 0, 0, and then a circle at 425, a circle at 23, 17, 13, negative 15, and negative 15, negative 7. I can then join all of those circle centers with a polyline, snapping to the center point of these circles. And with my closed polyline, change the color of these, with my closed polyline I can check the area to find we have 694.5, which is answer 5 there. You'll see that once you complete the problem, the user coordinate system is automatically moved back to its initial position. Okay, volume solve. So this is looking at the volume of a sphere which has a cylinder subtracted from it. So a cylindrical hole of radius 17 is concentric with, so concentric, sharing a common center, with and passing through a sphere of radius 33. So start with the sphere command. Going to draw a sphere here of radius 33. Might help me to change my view as well. So I'm going to go in here, change the view to conceptual, so you can see a bit more of what I'm doing. There we go. Okay, now I'll close the ribbon again. So this is my sphere, and I need a cylindrical hole concentric with that sphere. So I can supply the cylinder command. I can snap to the center of this sphere and specify a radius 17. Shift and middle click to rotate the camera. I then need to supply a height for this cylinder. Now it actually doesn't matter how high I make it as long as it's taller overall than the sphere. So I'm going to make it quite large and then move it down so that it's poking directly out of the sphere. You'll see that my tracking, if it says AutoCAD is telling me I'm tracking along polar at an angle which is just negative Z, so I'm moving in the negative Z direction. That means I'm still keeping my cylinder concentric with my sphere. And this is the shape that we're going to work with in a moment. So in order to find the volume of the sphere less the cylinder passing through it, we need to use the subtract command. So we can subtract the way this command works is you first select the objects that you're going to take something away from. So I'm going to take the cylinder away from the sphere. I select the sphere first and hit space, and then the next thing to select is the object which is being removed. So this is now my sphere less my cylinder. And finally, my answer needs to be given in terms of the volume of the solid. I can return the volume of any solid drawn in AutoCAD with the mass prop command. It defines the properties of a mass. Select that object and hit space. So I can see the volume of this object comes in at 94781 units cubed, or 9.478, so rounding up to 9.48. Oops. No, do not write analysis to file. This value here, answer 2, 9.48 by 10 to the 4 millimeters or units cubed. So 9.48 is answer 2. And that's the solution to that problem. Okay, only 2 more to go. So the centroid of a region, there are numerous times in engineering when you'll need to determine the centroid of a shape. So a complicated shape can be hard to find the centroid of, but with AutoCAD it's a pretty simple process. So the problem statement: the following region is defined by straight lines connecting 5 points. Move the user coordinate system to the centroid of the region. So again, the first thing we can do is type mass prop, and the mass properties, this region here will have a centroid about its according to its geometry. So mass properties will yield that centroid. And it can help to write this down if your memory is not the best for arbitrary numbers. So in X we have 603.19, and in Y we have 108.54. No need to write the analysis to a file. Now we need to move the user coordinate system to that point, but again, specifying UCS, we're given the option to supply a length and an angle more than a point. So I'm going to again draw a circle at that point. It was 603.19 and 108.54. Can now move the user coordinate system to this point, and unlike the multiple choice answers that we've had before, once you've moved the user coordinate system, you simply hit QE, and if you're within a small tolerance, that value is marked as correct. So finding the centroid is important, because if you want to determine the second moment of area, which has a large influence on the behavior of bending of a particular cross-section, you need to first make sure that you're calculating that second moment of area about the centroid. That's the nature of this problem. It's just getting you familiar with determining the centroid of a difficult region, moving the user coordinate system to it in case you need to determine the second moment of area. Which brings us on to the last problem, the determination of second moment of area of a solid. Okay, an I-beam. So an I-beam is a beam which looks like this. An I-beam has depth 66, flange breadth 25, web thickness 6, flange thickness 8, and fillet radius 3. Determine the second moment of area about the beam's strong axis. So an I-beam, it could be bending sort of about this line, so bending top to bottom, or it could be considered to be bending left to right. But because there is much more material about the cross-section which is separate from the neutral axis, when we're talking about the above and below case, this is referred to as the strong axis of the beam. So this axis here we're not particularly worried about. You may also notice that this object is doubly symmetrical. So this means it's going to be quite easy to construct. It also means that we know exactly where the centroid is going to be without having to first determine it from mass properties. For a doubly symmetrical shape, the centroid is right in the very horizontal and vertical center. So that's an easy one to find. Okay, so in this question you basically have two parts. You need to first draw the I-beam, so construct it correctly based on these properties, and convert it to a region. And then secondly, you need to determine its second moment of area about its centroid. So we'll start with depth 66, we need breadth 25. All of these values like B, F, and R and things, they are all labelled down here. You can see this is BF is the breadth of the beam. We have the total depth D. Coming back up here and back to there. Okay, I have a web thickness, so that's the web is the part that joins the top to the bottom. I also have a flange thickness of 8, so I'm going to draw the flange in now. I'll draw that with a polyline also. 8 and across. And if my web thickness is 6, that means from the center line I'm going to be 3 units either side. And I just want to go down to the halfway point in the beam. I'm going to take advantage of that symmetry of the beam in a second. So we also have that the fillet radius, the small radius of curvature between the flange and the web, is radius 3. So I use the fillet command, radius 3, and specify these two objects. And then I can make good use of mirror to copy that side left to right and copy this part top to bottom. Once I trim away the unneeded sides and join the whole thing together, I now have one solid closed polyline, and I can use the region command to turn this into a solid region. If I want to measure the second moment of area of this object, it needs to be about the centroid, so I move that UCS to the centroid, which, as I mentioned, is going to be in the center of the shape, vertically and horizontally. It's just because it's a doubly symmetrical shape. I can then use the mass properties of this object to find its moment of inertia, also read second moment of area, is 405 by 10 to the 5 units to the 4. So that's going to be this value here. Actually, if I just have another look at these mass properties, I just want to show again. So this is bending about the x-axis. This is the strong axis. You'll see that this value is 20 times larger than the strength bending about the y-axis. So hence the term strong and weak axes. So the x-axis is what you'll always need to supply for this shape. So yeah, 4.06 by 10 to the 5. Given there, answer 2. And that's all there is to it. So these 7 shapes, I think, are somewhat time consuming if you do them manually. If you do them in AutoCAD, I mean, I've been talking over them, but they're all somewhat low time. And even this problem here with the quite involved design things, if you're working quickly and making good use of mirror, you can get that done in not too much time at all. So I hope you all get plenty of practice before the upcoming test. So in week 12 we will work through this problem. This video, I hope, will enable you to get lots of successful work and answer any questions that you may have. If there are any remaining questions, just drop by the office and see me, or ask them in the tutorial. I'll see you all during the tutorials and also the week 12 lecture. Okay, thank you for watching.